All right, so I see everyone's coming in and settling down. Before we do the lecture between now and 12, I just want to do one more thing for the setup, just to make sure everybody is in a good place before we go into lunch. So for folks who successfully ran, who navigated themselves to the day 2 SQL Docker folder and successfully ran the docker compose up command, you may have seen something that looks like this. What I'm going to ask you to do now is the following 2 steps. Go ahead and run docker compose down. You should see something like this. Okay. Then I want you to run git pull, because I made one additional small tweak to the YAML file. Okay, so go ahead and run git pull. I'll do it myself here, although I'm already up to date. And then after you have run the docker-compose down command inside of the Docker folder, ran the git pull command to pull any further differences between your local repository and the session 21 remote repository, I want you to just run that docker-compose up -- detach command again, and it should look something like this. Okay. All right, I'll wait a couple moments. Okay, and once you have done, sorry, we have a. To pull, or which?
For the and I got the same thing for the Docker compose now.
Did you get that earlier or no?
Everything ran totally fine.
Did you turn off your computer and turn it back on? You might have to remember how you did the user mod command and then did the SU thing to sort of relog your trigger it. If you can find that user mod command and the SU command, run that again. Yes?
When I do the docker compose bit, I get versions obsolete.
Is it as a warning or an error?
I think it's a warning.
I
got it.
You got it too. I think it's just a warning of the file. Did you get the rest of the thing that said stopping and everything? Oh, no. Okay.
Oh, wait, you don't drop that.
Okay, afterwards you ran up.
Oh, I just did up now.
Okay, so that's fine. You're getting all the log file. If you do the -- detach, you don't get all that extra stuff. But, okay. So if most folks have made it to the point where they have successfully ran docker compose up -- detach, what I'd like you to do is to go to, in your browser, go to localhost :8888. Okay? So again, that's localhost :8888, 4 8s in your browser. And it should take you to a Jupyter Lab session where it asks you to put in a password or a token. Okay, so let me quickly skip ahead, cover all this stuff, but let me get this picture. Okay, you should see. Did I not have? Oh, okay. All right. So if you went to localhost :8888, you should see the Jupyter Lab homepage, and it says you need to enter a password, right, or a token. Your token is capital S session 21. Okay. Let me get myself to. Yes.
When you enter localhost 888, how long
It should trigger, redirect you to the Jupyter Lab interface pretty quickly. Yes, absolutely. So it should be in the top. It says like, what is your, can someone show me? Unfortunately, I didn't reproduce it. Somebody, you have it, great, awesome. Where it says password or token, and then with a login button at the top, you're gonna put capital S session 21. Oh, it just took you in? Oh. Oh, I see. Okay. All right. Yes, this is good. This is why we're doing this. Who here already was running Jupyter Notebook or Lab from the last session? Because if you were already running Jupyter Notebook or Lab from the last session, you must shut that notebook session down, or you will be in conflict with the container notebook session. So please go ahead and shut that notebook session down from the last session. So you just do Control C. So if you do Control C, now it's going to essentially run the down. So that's why you want to run the dash detach so that you get the and then detach, DETACH. Enter. And so it'll start everything up again. Now you just got your command prompt. So again, you go to the browser and you go to localhost :8888, just like you would for. Yes. Great question. We had a question from Marcus who wanted to know, how is Jupyter even running? Like, why would I know that Jupyter is running and where to go? So in Docker, you can see that one of the sections of the YAML file here is called Jupyter. And what I am doing is, containers, their big thing is they're supposed to be, isolated sort of environments that run on your machine. However, even though Jupyter is actually running inside of the container, here with this ports flag, I'm saying take port 8888 inside the container and expose it to my local laptop at the same exact port number. So Jupyter is actually not running on your Mac. Jupyter is running inside the container on the Ubuntu 20.04 operating system. And the beautiful thing about containers is that we have leveled the playing field. So there's no more your LSST environment versus somebody else's LSST environment. We are all running the exact same software environment down to the operating system. So you're in great shape. Yeah, please. Yeah, it's a good question. So somebody asked, what does Docker do exactly? So if people are familiar with in the past, right? If you had a PC and it had Windows on it, and you were like, I need to get Ubuntu on this machine, you had two options. You could either create a virtual machine, a full-on virtual machine, where you're like, hey, I'm going to install Ubuntu, the entire operating system, in this little virtual machine. I'm going to give it 2 CPUs and 4 gigabytes of memory so that it can run at the same time that my Windows runs, right? Or you had to do something even worse. You had a dual boot, which means you either booted into Windows or you booted into Ubuntu, but you couldn't have both at the same time. Docker says, let's do away with all of that stuff. Let's take all the best parts about virtual machines, which is that you can basically spin up any operating system you want on any machine you want, but not interfere or deal with all of the annoying parts of trying to set up a virtual machine. Because as you can see, even though Docker is running on all of your Mac and Windows and even Ubuntu machines, this is not getting in the way at all of me running PowerPoint or doing any of the stuff on my native operating system. The other best part of it is, again, the word container is you can bring it from machine to machine to machine. So if you have ever experienced, which I'm sure you have, we had IRAF yesterday, we talked about IRAF yesterday, how difficult it can be to replicate application or software environments as you move from your laptop to a high-performance computing center to your colleague's laptop, right? They're not portable. Software environments are generally not portable, but containers are. Sorry, Marcus had a question first.
So I'm still confused, though. Like, there's no clear indication that the Docker is serving my Jupyter lab at this port.
Okay.
You get what I'm saying?
Yeah, I know. I understand. Enter the Docker file. You can only build a container if you have explicit directives or instructions to build a container. And the most important part about building a container is at the very end, you tell Docker, hey, after you've done all these installation commands from lines 1 all the way to the end, what's the actual thing I'm running when I run this container? So basically, like on your own Conda virtual environment, right, what would you do? You would go, here I have Anaconda already, right? I would run Jupyter Lab, blah, 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 something, 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 and that would spin up the Jupyter server, right, the notebook server. And basically, you're telling Docker, run that same command that somebody would run from their own terminal. And then you're basically, this auto runs after you build it. Does that make sense?
Yeah, so it's running in the background.
Yes.
So I don't want to make a mistake where I forget that I have Docker running in the background.
Yes, okay. Yes, that's true. So that's where the desktop comes in handy. Because in case you totally forgot or don't realize what's happening, you can see like, oh, cool. Docker is letting me know, actually, you know what? I have these 3 different containers all running at the same time right now. Okay. Yeah. So it tells you have a Jupyter container running, a SQL server running, and then an SQL admin server running. Yeah, go ahead.
So this Docker container, it's on the Docker container, it's on our local computers, local machines. So when you actually run code, which CPUs are being used?
It's a great question. So it is basically, so Docker, unlike some other container applications, where other container applications seamlessly interface with your hardware, which basically means like if you're on an HPC system and use Singularity to run a container, it has access to all the memory and cores that you have access to on that machine. It's like a seamless thing. Docker says, well, that sounds nice, but probably you don't want Docker taking over your whole computer. If you would like Docker to take over your home computer, you are more than welcome to take these sliders and tell it that it has access to all the memory on your computer, it has access to all the CPUs on your computer. It would be happy to run those containers on the entire hardware resources of your machine. It kindly doesn't do that by default because it assumes you're probably doing other things on your computer and don't want it to just crash. But you could. Go ahead. Did that answer your question, by the way?
Yeah, and would it be similar when you're using a cluster with Docker?
So clusters, HPC clusters don't let you use Docker. Who can tell me one reason why they don't let you use Docker? Root privileges. Okay? That's where Singularity or Apptainer or some of these other weird-sounding software come into play. They interface seamlessly with containers built with Docker, but they're for use on HPC or cluster systems because they don't require administrative privileges to run. Docker requires administrative privileges to both build the container and to run the container. These are all great questions, by the way. I love that we haven't even gotten to SQL here. Yeah, great question. So the question, just to repeat the question is, okay, Singularity, you can pull a Docker container with Singularity, but can you pull a Singularity container with Docker? In general, there's something called the Open Container Initiative, OCI, which is essentially designed to make all of these different container flavors. You might even hear of like Podman. There's like Podman, Singularity, Apptainer, Docker. They're all supposed to play with each other. They're also all supposed to play nice, even if they have their own, esoteric things. But in general, yes. Yeah, Jordan.
Yeah. Ooh, oh my lord. Hello. When we were setting all this up, you had a bunch of very specific files and structure that we had to get it all set up for our way. How much of that would we have to do to be able to set up our own? Is there a standard interface? Is there a default?
That's a great question. So we have, unfortunately, so in general, most people do not run multiple containers at the same time. You have a single software application that you would like to install in the container and then run from the container. Let's say a Python code that has a specific set of packages in it, and you're like, I want to make sure that my Python environment can be replicated anywhere I am on any computer in the entire world, right? You would build a single container, and then you would just keep reusing that container in different locations. We have used something that Docker can do that Singularity cannot, which is we've actually spun up a little mini server cluster. By running 3 containers at the same time, we've essentially emulated an environment in which we have 3 different virtual machines all running on our one laptop, which I just want to say is pretty cool. All right? It is very difficult to basically run this exercise where you are truly doing something you would do in real life, which is you essentially have a notebook that's making calls out to a database server. That would be very hard to do for 48 people, through the legitimate way you would do this, which is spin up 48 different servers, and then there'd be 40 different, 40. It would be very difficult to do. But you on your laptop are essentially running a mini production environment right now, a mini production way that things would be set up for databases. Did that answer your question, Jordan? Yeah. Because and that's where that Docker Compose YAML file, where you might be looking at that YAML file that I opened and said, oh, look at all these, there's an environment set in. You're like, that seems overly complicated. The answer is it is, doing this is overly complicated. Running just one old container with your code in it for reproducible purposes is really actually not overly complicated to do. This is a little overly complicated. All right, so just real quick check. If most everybody, do they make it to this page? And most importantly, you can't see it? Real quick, do people see the session 21 directory in that list of available directories? That's the important, okay, good, all right. So I think we're in pretty good shape here for after lunch. So I'll go to the lecturing part now. Okay. Okay. So, all right. So we're going to be talking today in the next 30 minutes here about 5 different topics. We obviously already skipped to number 5 here at the beginning for obvious reasons, which is that there was always going to be some hiccups for this, but it does seem like we had the vast majority of people able to spin up the Docker containers and access the Jupyter server that Docker is running. So we're going to cover, just again, briefly cover tabular data again. That was already covered this morning. We're going to talk about all of the jargon that goes into SQL. There's a lot of jargon. When someone says MariaDB or MySQL, that involves something called the database server. Just the phrase database, what is that? Schema, you might hear. You may even hear the term relations. What are all of these things? What is all this jargon in like human understandable terms? Then we're going to talk about the actual programming language, structured query language, which is what SQL stands for. It's basically, the name of the game is people have databases because there is information such as, how many films did Martin Scorsese, direct? There's information people want out of these giant tables, and they want it as fast and effectively as possible. Then we're going to talk about Django, just one of many Python applications, because again, what you're going to, I think, probably feel like after seeing the structured query language is be like, so wait, I have to learn an entirely additional programming language just to interface with databases? And the answer, fortunately, is no, because there are a lot of Python applications that do a great job of interfacing with databases in a Pythonic way so that you don't have to be, dealing with learning an entirely new programming language. Okay, and then we'll go finish up the few issues we had with Docker Compose. Okay, so much like the slide from this morning, what is the most important tidbit of these 4 CSV files, would you say? Similar to the tables that we saw earlier today that had astronomy data on them as opposed to Internet Movie Database data. What's the most important thing that you see from here?
The movie title.
The movie title is important. So there's the column names, the headers, that's important. That's the IDs, yes, the IDs and the repetition. So what's very important with any table or sets of tables is that all of these CSV files relate to one another. Okay? And as was noted with the repetition here, more in the genres, I think, than anything, right? The reason why there isn't a column genre in the table for movies is because a single movie can have multiple genres associated with it. It does not have multiple name, year, and IMDb rank. There is one IMDb rank, one year, and one title, per movie, right? And so again, that key phrase is, and we'll talk about later today, is relations. All of these CSV files have clear relations with one another via their IDs. And so, as I mentioned earlier today, you would not want to have the movies table have 2 entries for movie ID 1 just so that you can repeat the row genre multiple times and unnecessarily inflate the size of your table. Okay? So what if you had something that could not only manage all of those CSV files or tables, i.e. doing things like adding new rows in a way that's like once you add a new row to the movies table, right? What do you also have to do when you add a new row to the movies table? You have to add it to all these, because it's got a genre, it's got a director. The directors in movies need, you can't just add a row in one place, because there is no such thing as just a movie coming out isolated, right? It has to properly be added to the rest of the whole system. Yeah?
This is kind of an aside.
Please. Well, we spent most of the time talking about Docker for the first 30 minutes, so that's no problem.
But I was just thinking about it. Do you really need directors one? Because isn't there only one director for each of the movies, and then each of those columns for the director movie ID is the same thing as putting the director's name multiple times in the movies?
So that's a great question. So what's included in the director ID, or in the director's table though? Because it's more than just the ID. There's a lot of metadata specific to a director. So if you had to have the director data, so like here, right, you can see that even in this first one, right, whoever director number 3 is has obviously, directed multiple movies. And so that would be an expansion of basically like this, what I'm saying is this linking table has bare minimum information in it, right? One column is an integer and the other column is an integer. That links basically this to this without repeating any unnecessary information.
I guess what I was saying
Yeah.
was you can get rid of director ID, and movie ID, and compress it to just two like first and last name, which is essentially what director ID and movie ID is, 2 columns. And then anyway, sorry, it's an aside, and then put it into movies. I guess was what I was saying, but this is totally an aside. Sorry.
Some of the movies do have multiple directors.
Oh, do they? Okay, so maybe that's the reason.
Yeah, definitely some of the movies do have multiple directors as well. But I do understand your point, and that's the right mindset to come into this whole process with, right? Like if you're going to go down this road, you do want to be very intentional about how you're setting up these relations. So why have I kept saying the word relations? Because when somebody says the word relations as it relates to SQL, they are just referring to tables. That is a fancy SQL word for a table. Okay? So basically, as I mentioned, it sure would be nice if something could handle all of these tables in a sophisticated way. And that's where something called a database management system comes in handy. And a database management system sounds unnecessarily fancy, and in many ways it is. It's just the reference to this whole suite of software that you may have heard of. My guess is the ones you've heard of is MySQL and possibly PostgreSQL. But if you're more Windows oriented, you might have heard of like Oracle or the Microsoft database management system. The ones that you're really dealing with in this area are going to be your Postgres and your MySQL database management software. Okay. So again, we're going to cover the jargon really quick. Okay, so there's just jargon for days and days and days when it comes to databases and database management systems. So you have the server. People refer to the database server. They'll refer to a database. They'll refer to a database management system. They may even refer to relations within a database. That's the tables. They may talk about the attributes that relations have. Those are the columns of the table. They may even refer to the domain of an attribute. That is the constraints on the values that a given column can have. So who can think of a perfectly reasonable domain that you would, quote unquote, domain that you would apply to a column in an astronomy table?
If you have like an absolute value for fluxes, if you...
Sure, or like RA and DEC, right? Like RA and DEC, they can't be infinite values, right? They have to be between 0 and 360, right? Or whatever your units are. Okay, so all of this fancy terminology is just basically saying, like, again, this is that intentionality. Tables and databases are all about being hyper-intentional. If you're going to make a column called RA, you got to specify what is the type that it can take, so like a degree, right, a unit of degree, and you have to say what are the minimum and maxes that it can take. Because all of that, you might say, like, why do we have to be that specific? All of that information directly correlates with how big your table becomes. And big, I mean literally how many like megabytes, gigabytes, terabytes, petabytes big your table becomes. Because who can tell me if you name a column and you say, double precision float, that covers all numbers, right? I love values that can literally be all real numbers. And yet that column only contains integers. That's like the only realistic value that that column will ever be of that table. You have just unnecessarily like doubled, quadrupled the size of each entry into that table. Which again, at the scales of 1,000,000 rows, all good. At the scale of 27, or 37 trillion rows, not all good. Not good. Okay? So, what is the server? So someone might say like, hey, I got a database server. Okay? So it is the physical or virtual machine where the database and the database management system actually live. Like where they're actually running. So someone might say like, hey, I have a database that runs on like mydatabase.sierra.northwestern.edu. Like my database.sierra.northwestern.edu is some virtual machine that is somewhere, in this case, at the Northwestern Data Center. And that's the physical, or in this case, virtual machine that the database runs on. Then someone is going to say, hey, I got a database. I got a pretty sweet database. And again, a database is just a structured collection of data residing on a computer system, so on the server, that can be easily accessed, managed, and updated. So what does that really mean? What that really means is that a database is a set of tables. So the reason why someone might have multiple databases is because, let's go back to this. Would it make sense to have one database that has tables related to IMDb data and on the same exact server have a database related to LSST telescope data? Like to put these tables and the tables we saw earlier under the same database umbrella? The answer would be no. That would not be very sensible to have one database and tables related to like all sorts of random topical stuff. So you would want to have one server that hosts multiple databases, each database a collection of tables that makes sense for, let's say, telescope A data goes inside of one database, telescope B data goes inside of a different database. Okay, we talked about the database management system, so don't worry when someone says MySQL or PostgreSQL, they're just different flavors of software that does all of this database management for you. Okay? So what does a database management system do? Like what are we really talking about here? Okay? This is my favorite part of database management systems. It provides concurrent access. Okay? So when you have that Gaia data and you go to that fun Gaia portal where they let you enter an SQL formatted query and you click like return to me the answer to my query, you and about 1,000 other people are probably also clicking like the search button at the same exact time, right? And a database management system is set up to handle that kind of like multiple people asking for, basically queries at the same time. The other thing is the scalability. So again, as we talked about, if you're using CSV files or, Excel spreadsheets at a certain millions of rows, or even hundreds of thousands of rows, the efficiency you get in terms of operations you would do, like basic operations, like find the average of this column. I just want to know the average value of this column. That's going to take forever to do in Pandas or in Excel or whatever. To find the average of a column with millions, billions of rows in an SQL situation, It's going to be done in a snap. Okay? It also provides an extra layer of security because you can basically say like, hey, people A have access to this one particular table within my entire database management system, but people B have access to multiple tables. So you can be very intentional about who you're providing access and what kind of access, because who can tell me what the most tricky part of providing concurrent access to a table might be? Exactly. It's the rights. So when I want to, and Marcus wants to, insert a new row into the same table, who can tell me when you're doing that to a CSV file, what's probably going to happen? The word starts with C. Corruption. That's right. That CSV file is going to get corrupt, and if you didn't back it up, then you are out of luck. You're trying to do multiple concurrent inserts of new rows to a table that's managed by a database management system. It will always handle it. Okay? All right. So how do we model our data? And of course, our data is going to be modeled with tables, or sometimes they're called relations. So data is organized as a set of tables. Each table has a set of attributes, i.e. columns, and each column has certain constraints. So certain like types, like a character or a float or an integer, and then certain values that they can or cannot take. Okay? So again, I like the one from earlier today a lot better in terms of the example with the object ID of the RA index and then the time series in the other table, but this is a similar model. Okay. Finally, you might hear this word schema. I wouldn't worry about it too much. So basically, a schema is a situation in which you have a database. That database is full of tables. But maybe you would like to basically subgroup those tables together. But you don't want to create a whole new database and put the tables in a brand new database. You just want to essentially subgroup tables together. So what would be an example of that? Maybe you have, IMDb data, and you have like one table that has like super obscure information, and you want to kind of keep that table off to itself, and you have a schema. You might say like important information schema, and you would have all the tables that contain what you consider to be important IMDb data together in one schema, and then you'd have another schema called like unimportant IMDb data, and you would group those in their own schema. Now don't worry, schema, relations, database management systems is a bunch of jargon, okay? You can kind of visualize it here, okay? So this is a portal that you all will be able to access to through the containers that you're running. But basically, you can imagine I have a server. I've called my server the Internet Movie Database. Copyright infringement, for sure. Within that database server, I have a database, the IMDb database. Within that database, I only have one schema. I only have one naming of tables. It's the default naming of tables. And within my default naming of tables, I have a set of 4 tables. The directors table, the movies table, the movies and directors pairing table, and the movies and the genre pairing table. Okay? So you can kind of see that hierarchical flow visually better than in the words. And again, everyone's going to be able to access this, and they can kind of play around with their own thing. So what do you notice about this, this graphical user interface, and sort of as I go down and I expand, what's something you notice about this? Because there's one other super cool part about database management systems and about SQL. Does anything stick out to anybody?
Hierarchy.
Hierarchy? What? Oh, sorry, from Zoom? Okay. Can you repeat that from Zoom?
I said hierarchy.
Yeah, the hierarchy is important. Oh, sorry. Oh, no, it wasn't from Zoom. It was, yeah, sorry. Couldn't see. My apologies. So the hierarchy is, it's very structured, it's very hierarchical. That's true. What I was pointing at is maybe some of the words and phraseology and like weird tab options that I didn't box, because I didn't talk about any of those words or
I guess it allows you to select only what you want to view, so it reduces, I guess, how much you have access to or how much you're trying to read at one point, so like memory saving or whatever. So
that's true. There's definitely, you could see in this hierarchy how you'd provide those security or those specific access things. What I was looking at were more of these things like functions and aggregates and operations and stuff. You can base it, like there may be a particular, let's say there's a particular arithmetic that you want to always perform on your table. But of course, that value will change every time you insert a new row. So what would you have to do in a traditional situation? You would have to, if it was a CSV file, you put a new row in. You have to launch Jupyter again. You got to read the whole thing with pandas. You got to rerun your cell. You got to do all this work. Whereas you could instead just define a function that you want to run on the table all the time, every time there's a new row, and you just want that to be outputted somewhere. So this can essentially dynamically keep churning out and doing different calculations with each additional new row. Sorry, go ahead.
I was gonna say, wow.
Yeah, no, it's very, no, absolutely. It's super cool. And if you can even do something cooler, you can have essentially a whole column that's not a real value. So what I mean, it's not real. There's only real things, What I'm saying is that let's say you want column C to essentially be columns A and B multiplied and divided by each other. It's sort of like a meta value, because it only has a value based off of the values of column A and B. You could have column C essentially set to an operator, some kind of function, so that it's always, column A plus column B divided by, column A times B. That's what the value of column C is going to be. And it will just do that kind of calculation with each insert. Yeah? Sorry. Okay.
So is that value from column C stored at any points?
So it's a good question. It depends on how you've set up your database. So the name of the game in databases is keep everything in RAM. Keep everything in memory. Try not to put anything on disk. Disk is slow. Your hard drive, even your solid state drive, is slow. Your random access memory, or RAM, is fast. So it depends on how much RAM your virtual machine or physical machine has, and whether or not SQL can essentially hold it in that RAM, in that memory, whether it's like sort of ever actualizing that value physically. Yes?
I was just wondering about the event triggers. Would that be something like, we observed a new object or something, add it as a row to the table?
Event trigger would absolutely be like, hey, this object ID has never shown up before. It's a new object ID. Probably if you have a brand new object ID, there's a lot of things that need to happen after you have a new object ID, such as I was mentioning before, it may need to have an entry in table B. Tables, you might need to do a bunch of things if there's a brand new object ID that's been added to a given table. Now, again, I just want to be clear here, as I was telling Melanie this morning, I haven't even scratched the surface of any of these outrageous operations and things that you could do. I'm pointing them out not because I could right now live set up aggregation or set up an event trigger, arbitrarily. I'm just saying it's this kind of functionality, which is why people, move away from a CSV file and go to the big leagues, so to speak. Now, as I was also telling Melanie, who can imagine if you have all this sophistication going on, you got 30 trillion rows, what would a person worry about? What would a person might worry about? Sure, absolutely. Basically, you would worry about people performing operations that may cause bad things to happen in any of these triggers or any of these aggregations and your database server falling over. Because just like any old physical machine or virtual machine, it can and will die and fall over if it's being asked to do too much at once, which is why these databases tend to be highly guarded. For instance, in Gaia's case, that's why they don't let you just enter any old query and fire that sucker off to Gaia, right? They put some guardrails around their database because they don't want you to sort of overwhelm it, right? These things are still fragile and can be overwhelmed even though they are quite resilient. Okay, so now, what we're going to do here, because we only got five minutes, is I just want to show, again, some of the language you would use to interface with these tables. So if I wanted to get the columns of name and constellation from the database, from the table star, where dec is greater than 0, and I want to order it by the row vmag, this is what this is how you would do that in SQL, essentially. Okay, so the select statement allows you to select rows, particular columns from a given table with some sort of filtering, some sort of conditional statement. Okay, and you'll notice, the most important thing you'll notice is I have a conditional selection on a column dec that is not one of the columns that I have returning. So you can order by columns and query on column data and not actually return the values of those columns. You can return the values of whatever other random columns you want. Okay? The star symbol says, hey, I want all the columns. I would like all the columns from the table star where RA is between 0 and 90. Okay? So what is kind of nice about SQL, about structured query language, other than the fact that it's a whole different language that you're learning, is it's very, it's like spoken word, Like if you were going to design a language where you spoke something into existence, you'd be like, oh, I'm going to select column A and column B from table 1, and I'd like it where all the rows, the dec value is greater than 0. Like you literally just speak it and then you type it out. And that's kind of how SQL flavor works. So let's do a join statement. So here I'm going to, I would like all of the columns from the IMDb movies table. I would like to join on the IMDb movies genre table. And I would like to join on the column that they share in common, which is the movie ID column. Or in this case, the more Astro one, I would like to select all columns from table star. And I would like to do it where the column stellar type is the same as the column stellar type in table stellar types is the same as the column ID in table star. Oh, crap. Yeah. I reverse that. Where the column stellar type in table star is the same as column ID in table stellar types. Okay? So you can see that with select, you're kind of like, yeah, okay, I kind of speak that out and I do a selection. And then as soon as you try to join multiple of these tables together, these SQL queries sure get a lot more complicated looking. Okay? So again, when you're just trying to do an operation on a single table and you're not worried about joining a different table, things don't look so bad. But as soon as you try and do joins, things look a little bit tougher. And so what we're going to talk about in the afternoon, because I got to go through all of these. These are just like, again, this is just the SQL language syntax. We're going to talk about Django, which is that, okay. Yeah, please.
On join, is that very similar to pandas join?
It is very similar. Actually, most everything in pandas was somebody who used to do SQL and said, "I'll make pandas."
I'm very happy.
And so the main issue is the way that you do the join, because you don't have like a physical data frame A and a physical data frame B and do a dot join between the two. You sort of like join them together in memory. It performs like a query and then returns a thing. That's where it gets a little tricky. So again, I know we have to go to lunch here because it's 12 o'clock. But can anyone tell me, this is a big stretch, but I'm just curious what I get. Do any of these printouts, either from the CSV or from the table itself using SQL, make you think of anything from a Python programming perspective? Abstractly. Indexing, okay. Others? Objects. Objects. See, I didn't even have to get the hint. That sure looks to me like a table could be thought of as a class and the columns as its attributes to that class. And that's where something like Django comes in to say, like, hey, I don't want to make a new table, but you know what I'd love to do is make a Python class and have somebody else translate this Python jargony syntax into whatever the SQL nonsense is. And that's what something like Django is doing for you. So here, instead of figuring out how to make a table inside of a database using SQL myself, I just say, I have a class called IMDb Movies. It is going to have column movie ID with this type, column name with this type, column year with this type, and column rank with this type. And then Django does all of the work translating that class into a table that would actually go in an SQL database. And then it also allows you to then perform queries, which is the exercise we will be doing after lunch. So we will be performing SQL queries, and we'll be performing queries using Django. All right, so we're at time.